Hey folks, as you probably can tell, I'm not there today. So let's go through the material anyway. First of all, if you look over on the screen here, we've got today's picture is a dragonfly wing. This critter kind of found the wrong side of my uh, bumper, and I couldn't let it go to waste, so it now has found the right side of my camera lens. So it's a dragonfly wing, and there we go. Review from last week. We've got water being H2O and oxygen is O2, carbon dioxide, CO2, and the great big scary one, C6H12O6, glucose or sugar. And today I want to spend a little bit of time making sure you understand what ATP is. Before that, let's kind of review how we got here. Photosynthesis, you can see in the picture, we've got sunlight striking a leaf. We've got carbon dioxide that comes in through the stomata on the underside of the leaf. Water comes up from the roots, and the glucose that's made through photosynthesis becomes part of the plant. Just the opposite's happening in respiration, and that's really our goal, or one of our goals for today. In respiration, the glucose and oxygen go into the mitochondria, and what comes out is carbon dioxide and water, but in the process, it releases energy in the form of ATP. And we'll try to understand what that means here in just a second. So let's put the big scary equation up there. In the mitochondria, we've got glucose and oxygen combining, and they're going to give off carbon dioxide and water. And in the process, a whole bunch of molecules called ATP are put together. And this is what I mean by being put together. You'll notice in the diagram, I want you to watch two things. Over on the left-hand side, you can see the letters change from ATP to ADP. And you'll see on the middle of the screen, we either have 3 phosphates or 3 Ps or 2 Ps. When you see 2 Ps, the letters are ADP for diphosphate. And when there's 3 Ps, it's triphosphate, like a tricycle. So what you really need to know from this is that it takes energy to attach that last P onto the molecule to go from an ADP to an ATP. Once it's on there, once it has its energy, now that molecule is going to float all the way through your body, every single thing you do. Even those of you who aren't paying attention right now, you're using ATP to not pay attention. I don't expect you to know what this molecule looks like, but let's put a model in your head that might help you understand. So we're looking for something that's going to help us show that when we do something, it's got energy, and then that energy can be released. And here's what I'd like to think about. So if you've ever had the great privilege of setting a mousetrap, particularly an old school mousetrap like this, you know that when they are set, like that is right now, you want to treat them very carefully. They have a lot of energy that could hurt you. After they're snapped, like right now, you can pick them up and do anything. So the mousetrap that's been set is kind of like ATP. It's got lots of energy. The mousetrap that's been sprung is like ADP. It doesn't have much energy. Last year, I had students try to, well, it worked for them. They remembered ADP simply by reminding themselves that when the cell phone is got a dead battery, it doesn't work. So ADP becomes a dead phone. Now, some people take this to a little bit of an extreme. You may recognize this gentleman from a video we did earlier in the year. He's the one that was swinging his tennis racket at large globs of Jell-O. And if you notice, he hasn't changed his shirt yet. A little disgusting, I'd say. All right, so ATP is a molecule that's got lots of energy, much like a set mousetrap has energy. That's all we're going for there. It's used for everything you do, including thinking. So, depending on how you punctuate this, Some people might read this as a question or a questioning statement. I think I use ATP. I prefer to think of it as two statements. I think, and I use ATP. Let's make this look big. Starting over on the green side here, if you were to count how many times oxygen comes in from, or excuse me, carbon dioxide comes in from the top and water comes in from the bottom, about every sixth time from the chloroplast, you will see somewhere right about where my pointer is, you'll see a big old glucose molecule slipping out of there. So we've got photosynthesis going on, and it takes 6 pairs of carbon dioxides and water to make that one glucose molecule. That one glucose molecule finds its way over to the mitochondria and converts it back into carbon dioxide and water. But take a look at what's happening to the ATP. The ATP is heading off to the left. The whole idea here is that where the molecules may be cycling, they're going around in circles. They're just getting reused like a bunch of Legos. The energy starts at the sun, finds its way to the chloroplast, is then into the glucose. Glucose carries the energy over to the mitochondria. The energy then becomes part of the ATP, and that heads out. Energy only moves in one direction. Matter cycles over and over again. It's probably the most important thing we're going to teach you all week. Matter cycles, energy flows. All right. The other thing we want to know, what Homer Simpson here already knows, is that we can't create or destroy matter, we just rearrange it. That's what photosynthesis and respiration has been showing us. You can't create it, you can't destroy it, it only changes form. Later on in the day, later on in the class period, you're probably going to need to know this statement. But if you look over on the side of the classroom by the flag on the would be the west wall, you'll see a poster that has this very same thing. And remember that. It may come in handy in, about 10 minutes. All right. Would you please take a moment to find this plastic covered document? In your case, the blue oxygens will be red. I didn't get a chance to convert the one we have on the screen here over to red, so we're just going to go with blue. If you have that in front of you, I want to point out a few things, and then we're going to use this document for a couple of things. All of the text written on top of the document is about photosynthesis. The text written on the bottom of the document is about respiration. Over on the left-hand side, you should recognize that we've got 2 hydrogens and 1 oxygen. This is a column of waters, H2O. We've got 2 oxygens and a carbon, and this is a collection of carbon dioxides. Over on the other side, we've got pairs of oxygens, and we've got one great big clump of things, and if you count them, there's 6 carbons, 12 hydrogens, and 6 oxygens, C6H12O6, or glucose. If we move from left to right, if we're combining water and carbon dioxide and turning it into oxygen and glucose, that's photosynthesis. If we move from right to left, we take oxygen and glucose and turn it into carbon dioxide and water, we're modeling respiration. Right? This document is going to come in handy in just a couple of minutes. Take a brief moment and look on the paper and see the yellow line, or look on the screen, see the yellow line down the screen. Can you tell me, can you kind of think in your head, how many oxygen molecules, oxygen atoms, are on either side of the screen? So, for example, there are 2 here, that makes 4, then 6, 8, 10, 12, 13, 14, 15, 16, 17, and 18. How many do we have on the other side? I'll give you a second here. right? Did you figure out that there's 18 on both sides? In other words, we didn't create any atoms when we went through photosynthesis. We didn't destroy any. There's the same number of oxygens on both sides. Let's see if the trend continues. How about the carbons? These are the black ones. How many carbons on the left? How many carbons on the right? Did you count 6? Again, we didn't create any atoms. We didn't destroy any atoms. Law of conservation of mass. And finally, would you count the number of hydrogens? These are the white atoms in our model here. Did you get 12 on either side? Hopefully you did. All right. Back at this, let's just give you just another look. Photosynthesis is described up on top. It tells you up on top that photosynthesis takes place in the chloroplast. Down on the bottom, respiration, and it tells you it takes place in the mitochondria. And the spelling for all of those are right there for you. All right. Would you turn to this document? It says comparing photosynthesis and respiration. We're going to work through most of this together, and then we're going to leave the rest of it for you. All right. So mostly we're going to right now focus just on the top set of spaces. Notice there's a column for photosynthesis and a column for respiration. All right. Take a look at the column for photosynthesis. And if I go too fast, this is where whoever is the boss of you in there right now might pause the video in just a couple seconds. And that way it would give everyone a chance to get these items onto their table. So looking down the column here, photosynthesis takes place in the chloroplast. You've got the spelling on your plastic covered sheet. Which compounds are used in the process? Well, it uses water and carbon dioxide. Which compounds are given off? Glucose and oxygen. And what form of energy is involved? Light. So I'm just going to pause here, or your teacher will pause here if you need it, to give you a chance to get these 4 spaces filled in. All right. Let's take a look at respiration. Respiration takes place in the mitochondria. It starts with glucose and oxygen and produces water and carbon dioxide. And in this case, the form of energy involved is ATP, but instead of being at the beginning of the reaction, it's at the end of the reaction. Here again, if whoever's the boss of you in the room would just pause the video until you get a chance to get those answers written in onto your chart. I want to point out that photosynthesis and respiration kind of seem like they're meant for each other. They seem to be opposites. What photosynthesis starts with, respiration ends with. What respiration starts with, photosynthesis ends with. In other words, they're opposites. If someone were to ever ask you to compare, or maybe they're just going to ask you to write a sentence to compare photosynthesis and respiration, an accurate and very short answer might be that they are opposite reactions. Not a bad answer. They are opposite reactions. If you were to turn your paper over and look at question number 3, they are opposite reactions, period. Or not. The rest of this I'm going to leave for you. You should be able at this point to tell me the formula for carbon dioxide glucose, and oxygen. You should be able to tell me what elements are found in carbon dioxide, glucose, and oxygen. And you should also be able to tell me a use form. For example, in water, maybe the use is water skiing. It's kind of hard to water ski without water. Or drinking water, or as people decided to do last year, they talked about how it's very useful to dump over your, older brother. Probably not a smart move, but it might work. All right, this is where I'm going to stop. Hang on, not yet. This is where I'm going to stop. This is where you take over. There are 4 questions here, and your job is to answer them as completely as you can. If you look at the plastic covered document very carefully, you may find that the answer to question 1 and question 2 are right there for you. If you remember what I said before about comparing respiration and photosynthesis, you have an answer there. And the law of conservation of mass, if you don't remember exactly what it is, look on the west wall up near the flag on the whiteboard, not under the flag, but near the flag. You'll see a poster there. It's also on a review sheet that you should have at your desk. Write neatly so I can read it, and please remember to highlight any of the terms from the other side that you use. All right, that's all I have for you. I'll put another video together for you tomorrow, and be good.